Okay. Let's see, we were, I think, on the very last part of the planetary model. Yeah, recording. Okay. So just to finish up a little bit, I think we didn't get to this slide, but it's all about the electrons when you're talking about how two elements or two molecules um, uh, interact with one another. Now, notice that I kind of use the term molecule and element interchangeably. That's not actually maybe the best way to think about it. They both do this, but they're not the same thing. Um, and we'll probably get to this more, but element is just going to be that single set of atoms with a certain number. Molecules are going to be a number of those elements put together. Okay, so maybe they're already in certain um, formations, but it's still going to be the electrons that are going to interact. Um, uh, so you get various different properties, behaviors based on those electrons. Um, it's not exactly right when we describe it this way, so it is a little bit of an outdated model, and but it helps people to understand what's going on. Okay, so keep in mind this is a little bit simplified, but the whole purpose is to make sure that you don't have to get too complicated yet. And this is still taught this way, even in chemistry. And then as you go higher in chemistry, you learn that, oh, it's not quite exactly like that. And you've probably been through a number of things in other classes like that. You're taught a simpler way, and then you learn, oh, okay, it's a little more complicated than that. I don't know, maybe y'all had that in other courses. I know I have. Okay, so you've got to know atomic number, atomic mass, atomic weight when you're trying to understand an element. Atomic number is equal to the number of protons that the atom has, and that's a unique number for every element. That usually will tell you the number of electrons in that atom. Okay, why? Because if you know one and it's neutral, then you should have an equal number of the other. Okay, so if you've got two protons, how many electrons are you more than likely going to have if it's a neutral? Two. Okay, everybody's good with that, I think. The atomic mass is your sum of protons and neutrons. And the atomic weight is approximately equal to the mass of the element's most abundant isotope. And we're going to get to what an isotope is in a second. I'm trying to think about something I want to say here. I think that, for testing purposes, I'm going to focus more on atomic number and atomic mass. Okay, if you want to focus on those. For this class, I'm not going to put a lot of emphasis on the isotope. We're going to just mention it. And I want to give you some reasons why I think isotopes are kind of cool. But I'm not really going to hit on atomic weight. Okay, so the first two are the ones that I want you to make sure you know. So your hydrogen is the first one here. You've got hydrogen. So that's your proton, your electron. Here's helium. You've got protons, two neutrons, two electrons. Here's lithium. We've got, can't actually see that very well. Looks like it's got 4 neutrons, but there's 3 protons, 3 electrons. Okay, so if your number of protons changes, do you have a different element? What do you think? Yeah, That's the difference here, right? Got one red ball, two red balls, three red balls. Make sense? Good. Okay. So if you are I guess a particle physicist, and you shoot molecules at each other, and you were able to take one element and get another proton to attach to it, will that change the element that you're working with? Absolutely. Have we done that? Okay, I'm not a particle physicist, but it has happened. You may have heard of, and sometimes it's not always necessarily protons. It can be the electrons, but maybe if you heard of a hadron collider, I think it's in Switzerland. It's not familiar. Anybody? It's this huge, long, like tunnel thing they have, and they'll literally shoot molecules, or not just that molecules, but atoms or parts of atoms at each other. And what that's done, and we don't have a periodic table in here, there are a certain number of elements that we know naturally occurring, but we know of some other ones that have been made in that situation. Okay, and we just haven't found them in nature yet. Okay, so we know they can exist. Doesn't mean they're stable. Okay, sometimes they come apart. A little too much information there, probably. So isotopes, real quick, it's just atoms that have the same number of protons and electrons, but they vary in the number of neutrons. Okay, so isotopes have the same atomic number, but you get different atomic masses. Okay, and again, we're not going to focus on the atomic mass, but I do want you to understand the reason why I have weights, okay, and that's not the term what they want to use here, because weight is a result of mass and gravity interacting. Because you get different weights with different gravity, like if you're on the moon, you're going to weigh less, right? But you have a different mass. No. Okay, so I'm going to use the term weight, but it's not really weight here. You have less or more mass in this case. In a lot of cases here. And it's because you have a varying number of neutrons. And neutrons and protons have mass. Electrons' mass is almost negligible. It's not that they don't have any, but it's almost negligible, at least for our purposes. Okay, so hydrogen with no neutron, hydrogen with one neutron, deuterium, hydrogen with two neutrons, tritium. Okay, and we do use these for various things, and they can be found. They're all a form of hydrogen, but they're isotopes, different masses, because they have a varying number of neutrons. Okay, so you can get that. You don't have to remember this. Okay, that you'll see things like calcium. You know, its atomic number is 20, mass number is 40. It's just protons 20. If you've also got 20 neutrons, that's a total of 40. The atomic weight is going to be 40.078. Where does that 078 come from? Well, neutrons are actually where we get to 40 here. So protons and neutrons, protons, neutrons, and electrons. Okay, so does that make sense? Okay, but I mean, you can see just how much the mass is different between a proton, a neutron, and an electron here. Okay, so remember, I just want you to understand what an atomic number, let me go back real quick. It's the atomic number and the atomic mass, okay? We're not going to focus on the atomic weight, although we're talking about here. I won't test you on atomic weight. So what I think this is really cool, when you use isotopes, you can do things with radioisotopes. And you might go, well, what on earth? What does this have to do with any kind of anatomy? Well, we use radioisotopes for a number of things in medicine. So you have heavy isotopes of certain atoms. They tend to be unstable, and so we can actually, because they're unstable, we can measure how fast they, not sure if the right word is degrade. Okay. Have you ever heard the term half-life? So think about radioactive measurements. How do we date things? Really, 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 really long time ago. We can measure like carbon-14. Okay. And what that does is we have an idea of how long half of that carbon will stick around. Half of that will degrade. And then half of that, and half of that, and half of that. And we have a kind of measurement of how long that would be. And so we can see how much carbon-14 is there, and we can radioactively date things that were alive. You get to a certain point, you have to go to other isotopes outside of carbon, but you can do this. Okay, decompose. There's the word. It's on the screen. Not degrade. Decomposes to a more stable isotope. So it's basically just spontaneous atomic decay. I'm talking about radioactivity. And we can use this to tag and trace biological molecules through the body. Okay. So if you've ever had to have like an MRI and they inject you with something to like to detect as it goes through, it on face. This would be related to that. Okay. So that's why I think isotopes are really cool. Okay, molecules. Two or more atoms of the same element can be combined chemically. So in this case, hydrogen and hydrogen gives you H2, and H2 is what you're usually going to see available out in nature. Okay. Rarely are you going to have just hydrogen hanging around. It's just H. Okay. Why? Because it's highly reactive. It's going to react with something. It's going to combine with something. And in fact, it's so highly reactive, it's extremely explosive. Okay. Has anybody ever heard of the Hindenburg? Okay. It's a big kind of floating airship that was what allowed it to be able to float was the hydrogen. And unfortunately, hydrogen and oxygen, when they meet each other, they really want to become water. Okay. And unfortunately, that's an explosive process. Okay. And yeah, it's bad. Let's just say that thing went up in flames. Okay. You can look it up. It's a historical event. And that's where chemistry and history come together pretty badly. So you get reactants on the, so when you're looking at this right here, the left side of this arrow are the reactants, those things that react with one another. On the right side is going to be your product. In biology, although sometimes we'll use slightly different terms, I'm going to go ahead and add them here. This is more of a chemistry terminology. We will use the term substrate, okay, on the left. And usually because we're dealing with a more complex molecule that's going to do maybe a more complex reaction. But don't get confused if you happen to see the term substrate versus reactant. The substrate is going to be a reactant in this reaction. They both will give you a product. Okay, we usually use that term. Okay, so you've got a molecular formula showing two hydrogens becoming H2. Does anybody know what we call this arrow? So if you've got H plus H, how would you read this equation? H plus H not equals. You can think of it as equals. We use a different term usually. The term is yield or yields. Okay, so H plus H yields H2. Compounds, different than molecules, are two or more atoms of different elements combined chemically to form a molecule of a compound. So you're going to see this so if you've got four H's, four hydrogens, plus one carbon, you get or yields methane, CH4. I'm telling you, if you've got free hydrogen, it's going to react with whatever it can get its hands on. See, I can't even talk about science without anthropomorphizing it. Hydrogen doesn't have hands, yet we use that terminology. Have y'all noticed that? How we do that all the time? And I try to be careful not to use that when I'm teaching, but it's so hard because it makes sense to us. But yeah. Okay, so molecule versus compound. So sodium, it's a metal. Chlorine, it's actually a gas. When you get them together, you've got table salt. Which of these three is very unreactive and harmless, basically? Which you eat too much of. It's going to be your salt. Does anybody know what happens when you put sodium in water? Boom. Yeah, sodium metal we put in water is extremely fun. Okay, it's a little explosion. Okay. Never got to do it in real life, but I enjoy watching videos of it because no one ever gave me sodium to play with. Okay. So this is going to start leading us into chemical bonds. When we have chemical reactions like this, do y'all remember what I talked about with bonds and energy? Bonds store energy. Okay. The molecules we can make, but the energy we cannot. Keep that in mind, the laws of thermodynamics. So chemical reactions occur when atoms combine or dissociate with other atoms. Chemical bonds are energy relationships, okay? And I would love for you in your minds, and honestly, I'm going to write something on the board that just says energy equals electrons. And energy equals electrons. So if I ask you what is flowing through an electrical wire in this room, what is that? What is electricity? It's a current, but what is that current? Magic. It is energy, yes. So if it's energy, what is it? Electrons. Isn't it funny? I still told y'all that I wrote energy. I told y'all this, and it still took a few seconds for us to get there, right? Electricity, by the way, electricity is almost electron, right? Isn't that funny? We don't think about this, but just the movement of electrons is the movement of energy. And make it, but we can transfer it. And electricity is just the movement of the electrons flowing along those currents. So to some degree, this is kind of one of those places where you see electricity showing up in chemical reactions that may be in our bodies. Okay, that movement of electrons. And we have series of reactions that do that, but just continually electron, electron, electron. You may hear about the electron transport chain. If you've heard of that, we're probably will bring that up at least one point. But as one electron moves, that leaves an empty space for an electron to fill its spot, and it just keeps moving back and forth. So electrons occupy those electron shells or energy levels. We talked about those layers of electrons on the outside of the molecule, okay, or outside the atom. The electrons closest to the nucleus are more strongly attracted because they're closer, negative connected to that positive charge. It's the ones on the outside. We sometimes use that term valence electrons that we mentioned last time. Those are the ones that are going to interact. And that makes a lot of sense, right? It's because the ones on the outside, further from the nucleus, are going to be the ones closer to any molecule that's interacting. Okay. and it's two valence sets of electrons from one atom to another that interact. Okay, the two series of electrons that are furthest away from their corresponding nuclei. I am not going to require that you'll know the shells, okay? But there are multiple layers. I'm going to call them layers here, but we call them shells in chemistry. So you've got 2 and 8 and 18, and then you can have more electrons outside of that. Okay. So the ones that are going to be the most reactive are the ones on the outside. Sometimes it is shell 1 if you're in the hydrogen or helium. Outside of that, the shell 1 will not be reactive when you get to things like lithium and so on. It'll be the next shell. And as you get into larger, higher numbers, it'll be whatever's on the outside that reacts. That's all I want you to get from this. So that valence shell, the one that's on the outside, is what reacts. I'm not going to have you name these. I'm not going to have you remember those number of shells. Okay. One thing I do want to put here is at the very bottom. If you have a full shell of valence electrons, you don't form bonds. Okay. Have you ever heard of the noble gases? And if you're on a periodic table, they're all to the far right. Okay. If you've got a full valence electron shell, and the top one up there is helium, because that first shell's got 2, helium's got 2. When it's full, it's not reactive. Hence, you can blow up a balloon with helium and not worry about it exploding. But if you blow up a balloon with hydrogen, you're going to have a Hindenburg situation probably, unless you really care. Does that make sense? Why is hydrogen reactive and helium is not? Hydrogen has one of its 2 outermost shells full of electrons. Helium has both. And when you're completely full, you're unreactive. Okay? You need empty parts in your valence to interact. Basically, it's like, wow, I have an opening in my valence electron shell. How can I fill that opening? Oh, here's this other atom. They have some opening in theirs too, and they will share or take some of those electrons, hence reactions. Helium doesn't have that need, or any of those other noble gases. Does that make sense? Okay. So you can see that with helium, there's 2 here. Chemically inert, neon, also inert, because it's got 8 to fill its second shell and outer shell. Okay, not a big deal. I think that makes a lot of sense. The only thing I want you to get from this is called the rule of 8s, is that if you're full, you're not going to react. And usually you're full or stable when you have 8 electrons on that outer part. Okay. Of course, that's exception with helium, sorry, with hydrogen, because it doesn't have 8 on the outside. It's got just that's 2 spots. So if I just say that I've got a molecule or an atom that has 7 electrons in its outer shell, what do you think? Reactive or not reactive? It's reactive. Does it have 8 or does it have less than 8? So we can tell. Okay? That's all I want you to get from that. Let me ask you this question. If we wanted to colonize space, would it be important that we know these kinds of things? Why would we need to know this about let's say this. Let me start over. Have you all seen The Martian? Movie The Martian? Scott, oh, what's his name? Yeah, it is Matt Damon. So none of y'all seen The Martian. So what's really cool about the Martian is he got left behind on Mars, at least for a little bit. And there was a storm. I'll probably get into it anyway. It's worth watching. It's a good one. And the author that wrote the book is also apparently really good. I don't want to go back and read some good other stuff. I'm bringing this up because this main character, he's a botanist for one, which makes me happy. This main character botany, how's that ever happen? But it comes back to this hydrogen because what he decides to do is he's got to figure out a way to feed himself with the food that's left. There is not enough food. I mean, he seriously sits down and calculates the amount of calories. Calories is a measurement of energy. And he actually calculates how many calories he has to have on the assumption that if they come back for him, and I can't remember if he tries to contact them, somehow they figure out that he's back, and maybe he sends a message, but he calculates how long it would take. I'm not wrong, if they got back to Earth and then came back for him or something, I don't know. He calculates the amount of time he thought it would take for somebody to return for him, how many calories it would take for him to survive until that point. And he looks and sees how much food there is there. And he can calculate the amount of calories in that food. It's not enough. So what does he do? Well, he's a botanist. He decides to try to grow some of the food. So he unpackages things like potatoes. Potatoes are high in calories. Can he survive on potatoes? So what does he do is he takes his chemistry background as well and calculates how to get water to be able to grow those potatoes in a mixture of soil that he put together. It's really complicated. This is why I say, if you're going to try to colonize space, you're going to have to really know what you can put together and what you can't, what you have to be careful with and what you can't. Okay, because space is going to require us to understand stuff. And he actually calculates the amount of oxygen that he's got, the hydrogen that he's got available, and can he react it? And what did I say you get with hydrogen and oxygen? You get water. First, he needs the water to be able to water those potatoes and grow them, which I think is a fascinating thing. But it's totally chemistry to be able to survive. And all this is calculation of energy, calories, calorie use. It's really cool, I think, setup. It's a really neat movie, and I use it sometimes in some of my classes. But, and you can go look at this clip. I can actually pull it up and show it to y'all sometime if you want. But the first time he does this, he miscalculates and he blows things up because oxygen, they're reactive, and so he actually has to redo it. And you have to keep in mind, he doesn't have a lot of resources. He doesn't have a lot of room for error. So I thought that was kind of fun. So, but nobody's seen The Martian. I know. You have seen it? Okay. Do you remember this spot when boom? Okay. You can get that clip on YouTube. I use it in the class. I think it's a fascinating movie. I haven't had a chance to watch it because it uses a lot of this stuff that we're talking about. Because I mean, he has to have an understanding of anatomy. He has to have an understanding of botany, how to grow things. He has to have an understanding of chemistry for that all to fit together. Okay. So for things to be reactive, they have to have atoms that are able to lose, gain, or share electrons to complete those valence shells that have less than 8 electrons. Okay. The whole point is to become stable. Okay. So if you can fill your 8 by either losing, adding, or sharing with another molecule, you can achieve stability, and that is how you get products. Okay, that's how you get to those ends of those reactions. So hydrogen is reactive because it doesn't have both of its electron spots filled. Carbon is reactive. Let me ask you this. Look at carbon and look at the outer shell, and we said there's the rule of 8, right? How many electrons does it have in its outer shell? 4. How many should it have to be able to be stable? 8. So when carbon is reactive with something else, how many bonds do you potentially make with carbon? Like this. Remember, electrons are energy, bonds are storing energy. So in this case, when we talked about there only being 4 electrons, and we want to get to 8, so how many bonds can we make? 4. You see how we know that based on their valence numbers. So we talked about CH4, methane. So we've got CH4. So C has got 4 electrons. Each hydrogen has 1. And if they share them amongst each other, 1 electron from the carbon with 1 hydrogen, that fills the 2 for the hydrogen. The 1 from the hydrogen, from 4 hydrogens actually, with the 4 in the carbon, that gives them the 8. Now that's the simple way of doing it. But there are times when you can also get double bonds. So you're sharing more than 1. And that can happen too. But, okay. So oxygen is reactive. Oxygen is very reactive as well. Just look at things resting. And then sodium extremely reactive. Okay, y'all feel good about reactivity, valence electrons? Okay, am I going to make you calculate stuff? No, it's not the class. Okay. So what we just talked about was going to lead us into bonds. Bonds contain energy. There are a number of kinds of bonds. One of them is ionic bonds. And this is where electrons are completely transferred from one atom to another. So you actually lose it from one and gain it to another. And like always, we're trying to achieve stability. So ionic bonds are also ones that can, in some situations, disassociate with one another. I'll try to explain that in a second. So ionic is all about full transference. So what this does is a full loss or a full gain of some electrons. When you have a negative charge because you gained electrons, you're considered to be an anion. And if you have a positive charge because you've lost electrons, you become a cation. They tend to stay close together because they have opposite charges. So these are things that I always think about, like NaCl. Okay, you actually have a loss of electron from one and a gain on the other, but because one becomes negatively charged and one positively charged, they stay together. So it's an ionic bond because they become ions. Put that in water, they separate. Okay, so ionic bonds can actually dissociate from one another in solution like that. And I knew exactly that same situation here. You have your sodium, you have your chlorine. Sodium donates a full electron over. Why is it sodium that's donating? Sodium only has 1. And over here in chlorine, we're just missing 1. So it fills it up and basically empties that one out to the point where you now have a stable molecule. I mean, atom. I'm sorry? Is that what happens with water? Is that the reason why, like, H2O, we only need 2 hydrogen? No, it's actually what we're about to get to. It's another situation. So this one, the sodium completely loses that electron. In the case with water, if I'm not wrong, it is a sherry. Okay, and that's going to be a covalent bond. Here we lose it completely, and then they hang out because they're both ions, one's positive, one's negative, and they're attracted to one another. Put that in water, and they'll actually disassociate from one another. Well, depending on the solution, it doesn't have to be just water. Covalent bonds are different, and these are the ones that are actually more common, I think, in that's not true. How do I do this? I won't necessarily say that it's the most common, but I think more of the reactions that we deal with are going to be this, okay, in our bodies. So here we share. And these are extremely strong associations. Covalent bonds are very strong. If you share one pair, it's a single covalent bond. If you share two pairs, just like I showed the double bond, that's what you get here with two. So here is hydrogen. Okay. So what's the difference here? You've got hydrogen with one electron, another hydrogen with one electron. Does one of the hydrogens lose its electron? Not in the picture. The picture shows them actually kind of hanging out together. They still maintain their electron, it's theirs, but they're sharing it, and it creates a stable molecule. Here's oxygen, same thing happening here. Oxygen has got a double bond because it shares two on either side. Here is the hydrogen and the carbon example that we've looked at. And so they share. Do I need to explain that any further? I think that makes sense picture-wise. I don't have any questions. Okay. And with covalent bonds, you can have one of two kinds, nonpolar or polar. Now, same kind of bonding, but it's the result of how they bond after the fact that you get nonpolar or covalent, or sorry, nonpolar or polar. Nonpolar covalent bonds are when you have electrons shared equally between the atoms. Carbon dioxide is an example of this. And what that does is because they're equally shared, they're electrically neutral. I like to think of them as being balanced. Okay. And the reason why I think this is interesting is, I mean, just visually looking at carbon dioxide, is it symmetrical? Yeah, like if I were to divide the molecule into symmetry, I get a mirror image this way, right? And in fact, I get a mirror image this way as well. Okay. So this would be a nonpolar covalent bond. That means it's actually going to be very unreactive because it doesn't have any polarity. Whereas with polar covalent bonds, you get electrons that are not equally shared. And this is going to give you one side of the molecule that's slightly positive and the other side that's slightly negative. These are called poles, just like the North Pole and the South Pole. Water is an example of this because when you look at that molecule, is it symmetrical? It is this way, right? But is it that way? So here we've got a negative polarity and a positive polarity. So what does that mean for water? If you've got a slightly negative side and a slightly positive side, and I put another water molecule with it, what's going to happen to those two molecules? They're going to attract to each other. And they're going to attract in a certain orientation too, right? Positive to negative, positive to negative. Have y'all ever considered how strong water is? And it's because of the polarity. You ever think about that? Is water strong? Have you ever done a belly flop? Okay, water is solid for that brief moment, isn't it? when you hit it. It will separate for you after that fact, but it sure doesn't save your flop. Okay. Have you ever touched water? This, as a kid, you touch it. I would get water on my finger, and I would have some sputter. Right? This shows I'm weird, but I would take my finger and kind of like move it some, and I would watch the water droplet kind of pull down and then pull back up, almost like it was elastic. Water is attracted to each other because of its polarity. Water actually holds on to each other. Water creates surface tension, hence the belly flop when it hurts. But also, have you ever seen water bugs scurry across the top of water? I mean, are they magic? No, they just don't break the surface tension, and that tension created by the polarity, and they're able to use it. And for them, it's a semi-solid surface. Okay. See what I'm getting at there? Water's an amazing molecule. Okay, if we didn't have it, if it didn't have its properties, we would not have life. That's why it was so important that finding water on Earth parts of the solar system. Because if there is water there, there could be the potential of life, or the potential of sustaining life from Earth. Okay, without water, it's not happening. But water is so important. There's a lot of other things about water, not just surface tension. But water wants to stick with water. Okay. The last, well, I'm not sure if this will be the last bond. Let me see real quick. Yeah, we'll stop with this one. Hydrogen bonds are another set of bonds. We talked about ionic, we talked about covalent, polar, non-polar, and then the last one, hydrogen bonds. Very extremely weak, but extremely important because they help to keep things kind of attached. So when you've got hydrogen bonds, you've got, for example, when a hydrogen atom is attracted to a negative portion, such as an oxygen, having a go back real quick. So, like, do you see this kind of negative side on the oxygen? And then there's that positive on that hydrogen side. That creates that polarity. It's the hydrogen bonds that want to hold those two water molecules together. So polar covalent bonds hold oxygen together, but it's hydrogen bonds that hold those two oxygen molecules together. How can you overcome hydrogen bonds? How do you break the surface tension of water? How do we do that? How do we make it go from a liquid to a gas, for example? Heat it up. Okay. DNA, two strands of DNA that are held together by hydrogen bonds. And one way to actually break apart those things are to break them apart with heat. Now, our bodies can also do it with enzymes, but heat is one of those ways. So how weak is this bond? Very. Why does it manage to have a lot of control over molecules? Because you have a lot of those bonds working together. Okay, it's not just one hydrogen bond between two water molecules. It's millions, trillions of water molecules all attracted to each other with lots of hydrogen bonds. Same thing with your two pieces of DNA attached in two strands. You don't have one hydrogen bond, you have millions. Okay, and so intramolecular bonds, like we have a protein structure or the DNA strands, hydrogen bonds are extremely important because of that. Okay, and here you can just kind of see those orienting, and there's a picture here of the bug that's able to stand on top. Okay, I want to stop there because we got about 2 minutes left, and I don't want to go into the next part just yet. Y'all good to go? Okay. Any questions before we? Okay, I'm going to stop the share. Aussie, I'm going to let you go. I'll post the video later, guys. Okay. Okay, take care.